You've probably never even thought to ask this question. Why is space black? It seems too obvious to even wonder about, but the real answer is the most mind-bending than you think. Look up on a clear night. What do you see? A handful of brilliant diamonds scattered on a blanket of endless, perfect black. It seems so obvious, so natural. Space is black. But why? Why isn't it white? Or blue? Or better yet, why isn't it blindingly, terrifyingly bright? Imagine for a second an infinite universe filled with an infinite number of stars. Every direction you look, your line of sight should eventually land on the surface of a star. The entire sky should be a solid, searing wall of sunlight. The night should be as bright as the day. This was the argument of the German astronomer Heinrich Wilhelm Olbers in the 19th century, and it's known as Olbers Paradox. And the fact that it isn't true, that we are surrounded by this profound darkness, is one of the most important clues we have to understanding the true nature of the cosmos. The answer is not just about empty space, it's about the fabric of reality itself, the story of everything, and a darkness so complete it has a name: the cosmic dark. If we were to take a 19th century view of the universe, static, infinite, and eternally filled with stars, Olbers was absolutely right. The math is undeniable. Think of it not as looking at stars, but looking through a forest. If the forest is small, you can see through the gaps between the trees to the light on the other side. But if the forest is infinite and the trees are randomly distributed, then no matter what direction you look, your line of sight will always, eventually, be terminated by a tree trunk. There is no gap. Now replace trees with stars. In an infinite, static universe, every single line of sight from your eye should eventually intersect with the surface of a star. The entire night sky should be a continuous, blazing tapestry of starlight, with a temperature roughly that of the surface of the sun, about 10,000 degrees Fahrenheit. The fact that it isn't told us our classical understanding was profoundly wrong. So what's the shield? What protects us from this cosmic inferno? The first intuitive answers fall short. One might think, well, space is filled with dark clouds of dust and gas that block the distant light. And indeed, we have beautiful nebulae, like the Horsehead Nebula, that are dark silhouettes against brighter backgrounds. But this is a temporary fix. In an eternal universe, that dust and gas would eventually absorb so much energy that it would heat up until it glowed just as brightly as the stars it was blocking. It would become not a curtain, but a radiator. Dust can't be the final answer. Another thought might be that stars are too far away and their light becomes too faint to see. But here's where the geometry of infinity breaks our intuition. Yes, the brightness of a single star diminishes with the square of the distance. A star twice as far away is 4 times dimmer. However, in an infinite universe, the number of stars at a given distance increases with the square of the distance. Imagine shell after shell of space surrounding us. Shell 1 light-year away, might have 10 stars. Shell 2 light-years away, has enough volume to contain 40 stars. Shell 3 light-years away, has 90 stars. This is key. While each star gets fainter, the number of stars increases at exactly the same rate. These two effects, diminishing light per star but increasing number of stars, should cancel each other out perfectly. Every shell of space, no matter how distant, should contribute the same amount of light to our sky. A shell a billion light-years away contributes in total the same light as a shell 1 light-year away. Add up an infinite number of shells, each contributing a finite amount of light, and you get infinity, unimaginable brightness. The failure of this simple logical prediction was a quiet crisis in astronomy. It meant the universe we thought we lived in, A steady, eternal, infinite cosmos could not possibly exist. The darkness was a clue, a fingerprint of a deeper, more dynamic truth. The answer wasn't in the present arrangement of stars, but in their past, and in the very nature of the stage upon which they perform. The key to unraveling the paradox began not with darkness, but with light. In the 1920s, Edwin Hubble, peering through the giant telescope at Mount Wilson, made a monumental discovery. By measuring the redshift of light from distant galaxies, a phenomenon where the wavelength of light is stretched, making it appear redder, he found that almost every galaxy was speeding away from us, and the farther away the galaxy, the faster it was receding. The universe wasn't static, it was expanding. This was the first piece of the puzzle. Imagine the universe as the surface of an inflating balloon. Galaxies are dots on that surface. As the balloon inflates, every dot moves away from every other dot. There is no center. The expansion is happening everywhere at once. Now apply this to Olbers Paradox. The light from the most distant stars and galaxies isn't just faint, it's been redshifted completely out of the visible spectrum. The energy that those distant shells of stars should be delivering to our eyes has been dissipated, stretched into a form we cannot see. Our eyes are tuned to a very narrow band of the electromagnetic spectrum, and the expansion of the universe has taken the collective glare of infinity and pushed it into the infrared and beyond, rendering it invisible to us. This is a huge part of why the sky is dark. The expansion acts as a cosmic dimmer switch, turning down the volume of the universe's light over vast distances. But that's not all. The expansion also imposes an ultimate limit on how far we can see. Because the universe is only 13.8 billion years old, light has only had 13.8 billion years to travel. There is a horizon, an ultimate wall beyond which we cannot see, not because things don't exist, but because their light hasn't had time to reach us yet. But if the expansion and the finite age of the universe explain the darkness between the stars, it leads us to an even more profound question. What about the darkness itself? Why isn't the entire sky, even with a finite number of stars, at least filled with the first, most ancient light? To answer that, we have to push our time machine to its limits, to a time before stars, before galaxies, before even the atoms that would form them. We have to go back to the very beginning. For roughly the first 380,000 years after the Big Bang, the universe was a searing, opaque plasma. It was too hot for atoms to form. Protons and electrons bounced around freely, constantly scattering photons of light. Light was trapped, unable to travel in a straight line. The entire cosmos was a brilliant, foggy glow. Then, in a pivotal moment known as recombination, the universe expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms. The fog lifted. The photons, suddenly freed, streamed outward in every direction. This is the light we see today as the cosmic microwave background, CMB, the oldest light in the universe, a snapshot of that moment of first light. So we have our answers: the finite age of the universe, the expansion and redshifting of light, and the cosmic dark ages. Case closed? Not even close. Because when we account for all of that, when we add up all the stars, galaxies, gas, dust, and energy of the cosmic microwave background, we are still left with a shocking realization. We can only account for about 5% of the universe. The matter we understand, The stuff that makes up you, me, planets, and stars is a mere sprinkling of glitter on a vast, invisible ocean. The remaining 95% of the cosmos is made of stuff we cannot see, cannot touch, and barely understand. This is the final and darkest layer of our answer. In the far, far future, trillions of years from now, the acceleration driven by dark energy will ensure that the sky becomes blacker than it is today. All galaxies beyond our local group will have been redshifted into invisibility and pushed beyond the light horizon. The evidence for the Big Bang, the cosmic microwave background, will have faded away. The night sky for any future astronomers will almost be completely, utterly black, with just a few local stars dotting the void. They will have no clue that a vast, expanding universe ever existed. The darkness, then, is not just a relic of the past, it is the fate of the future. The blackness of space is the dominant feature of our universe. It is the visual manifestation of our ignorance, the evidence of a dynamic cosmic history, and the haunting signature of the unknown forces, dark matter and dark energy, that control our ultimate destiny.